You know that feeling when you're in a really intense video game? You see an obstacle, you react, it happens instantly. Total control. Now, what if you were piloting a multi-billion-dollar rover on Mars? So, what's stopping us from just doing that? That's the huge question we're going to unpack right now.
I mean, really, why can't we just hook up a joystick and cruise around the red planet? If the rover's camera spots a giant cliff dead ahead, why can't some pilot back here on Earth just slam on the brakes? Okay, let's get into it, because the answer is both super simple and completely mind-bending.
So, the problem isn't that we're missing some fancy new tech or a supercomputer. Nope. Our real enemy is just a fundamental law of the universe. It's called latency. And when we talk about Mars, we call it the 20-minute lag. And look, this isn't just a small delay. It's a giant chasm in time that changes absolutely everything. To really wrap your head around this abyss of time, we've got to compare two very different places. Because out in space, the real way to measure distance isn't in miles or kilometers, it's in time. And that time, well, it changes the entire game.
And this, right here, lays it out perfectly. Over on the left, you've got the moon. It's basically our cosmic next-door neighbor. A radio signal takes about 2.5 seconds for a round trip. Yeah, it's a noticeable delay, but you can work with it. The Soviets actually pulled it off with their Lunokhod rovers way back in the 70s. It was this painstaking, stop-and-go driving, but it was doable. But then, you look over on the right, Mars. That is a completely different beast.
So that 20-minute lag, that's just a handy average for the one-way trip. You see, since Mars and Earth are both moving, that one-way trip can be as short as 3 minutes or as long as 22 minutes. That means a round trip, seeing something and then reacting to it, can take anywhere from 6 to 44 minutes. That's not a delay, it's an abyss. And this just nails the problem perfectly. Let's run through the nightmare scenario. Your rover is cruising along, and its camera sees the edge of a canyon. That picture travels at the speed of light, but it still takes, say, 20 minutes to get to you. You see it, you freak out, you mash the brake command. That signal takes another 20 minutes to get back to Mars. So think about it. By the time your command finally arrives, 40 minutes have passed. The rover didn't just stop and wait for your instructions. It kept driving straight into that canyon more than half an hour ago. Game over. Okay, so if driving in real time is totally off the table, how did we ever make the early missions work? Well, the first strategy was pretty basic. It was kind of like trying to have a conversation across an ocean by just shouting really, really loudly.
Right, so back in the day, from the 60s to the 90s, probes would just point their antenna at Earth and transmit. This direct-to-Earth method was just brutal. The data rate was so slow you could wait hours, sometimes an entire day, just to piece together one single grainy picture. Think about that patience. And on top of that, you had the line of sight problem. If Mars rotated and Earth was on the other side of the planet, well, you couldn't talk at all. You just had to wait.
For the very first Mars rover, Sojourner, it was basically an exercise in pure faith. Engineers would bundle up a whole day's worth of simple commands, stuff like move forward 2 meters, turn left, check out that rock, and it'd send it all in one go. The rover would just store those commands and then execute them, completely blind. The team back on Earth had no choice but to wait until the next day to download the results and find out if it actually worked, or if the rover got stuck on a rock an hour into its day.
Obviously, this shouting thing couldn't last. To get the kind of amazing high-def science we get today, we had to stop screaming across space and start building a local network around Mars itself. And this was the absolute game changer, the orbiter revolution. Modern rovers use this brilliant two-step move. First, they make a super-fast local call to an orbiter, like the Mars Reconnaissance Orbiter, as it flies overhead. This is literally like upgrading from an old dial-up modem to fiber optics. Then, that orbiter acts like a cosmic data courier, holding on to all that data and then zipping the whole package back to Earth when it has a clear shot. But, and this is probably the most important point of this entire explainer, this amazing network solves the data volume problem. We can get massive amounts of information now, gigabytes of it, but it does absolutely nothing to fix the 20-minute time lag. The speed of light is still the speed of light.
So if we can't get rid of the delay, how do we solve the whole driving into a canyon problem? The answer was to stop trying to drive the robot at all. The robot had to learn how to drive itself. And the evolution of their self-driving ability is just staggering. You can really see the huge leap here. Yesterday's rovers, Spirit and Opportunity, they used a super cautious stop and think method. They'd move a bit, stop, take pictures, analyze everything, and then decide on their next move. It was slow.
But today's rovers, like Perseverance, use a system called AutoNav. It just drives. It keeps moving at a constant speed, using its cameras to build a 3D map of the world and swerve around obstacles in real time, without ever stopping. It's not just executing commands anymore, it's a robotic co-pilot.
So what's next? Well, we can't change the laws of physics. The goal isn't to get data faster, but to get more of it and more reliably. The next big revolution is going to be laser communications. Instead of radio waves, we'll use focused beams of light, which will boost our bandwidth by 10 to 100 times. We'll be able to get stunning 4K video from Mars, but here's the great paradox. We'll get that incredible 4K video, and it will always be 20 minutes late.
And this really is the ultimate takeaway from all of this. That 20-minute lag, it was never a bug we needed to fix. It was a feature. This impossible barrier, this law of physics, forced us to make an evolutionary leap. It made us stop thinking like we were just remote controlling a car. It forced us to start thinking about how to create a mind. We went from being pilots to being supervisors of intelligent, autonomous explorers. The lag didn't just teach us to be patient. It taught us how to build robots that can think for themselves.